I thought what is essential, maybe, in my part of the introduction, and I come out to just one topic. It's all about focusing. I mean, because we heard all about the tapping, which is, of course, very important. Lucas doesn't listen. But it's how can microscopy done better than the usual, very successful way as it was done here for hundreds of years. And all we know, roughly, in biology has to do with this instrument only. So, of course, there was a very important step by Stefan Hell, Nobel Prize, half of a Nobel Prize, to go below half the wavelength with microscopy. And since this is a school, who knows that STED microscope? Who has worked with it? Who knows what it is? S means stimulation. That means you excite. Do you need fluorophores here in your sample? You excite them to the electronic excited state, and you can't do it over a smaller width than lambda over 2, because you have far-field illumination and focusing. But what he then invented to do, he has a de-excitation. So it's a second laser, pulse, of course. After this pulse, there's this other pulse, and it de-excites all those excited states. So all these molecules are no longer active, but it excites with a donut mode, that in the middle of the mode, you have a 0. And now, because you go in a nonlinear regime, it counts very much whether you have full power out here or a tenth of the power or a hundredth of a power. But here at real 0, that's the only place where you leave the molecules unexcited, and that's where you then probe. And you can't do it practically smaller than lambda over 10, and it's a big success, but I say, but it's tedious to put the fluorophores in. Still, in biology, it's used a lot. And you should know this is what is called super resolution expensive instrumentation. Now, what I was thinking about a long time ago, can we do something which is easier, maybe cheaper, and doing things like we have it's now, of course, you know it all. We have a true super resolving color nanoscopy of things which do not even have to label in any way. Yeah. So, and at the end, I come also to the s-SNOM, use it in biology. That is sort of, was our news story last year, where I posted it. Anyway, the holo, I don't talk, of course, about the classical lens focusing, but two types of waveguides. The hollow waveguide, metallic, and the surface waveguide, also metallic. So that is also something of the past. It was great when it was invented, but you try to squeeze your photons, your pure photons down here into a channel which is too small for them to penetrate through, but a little bit leaks through. And so you still can go to a lambda over 10. And that is something which has the big con that if lambda goes up in the infrared, then it's uninterestingly small. What is so bad about the hollow metal tube? And this is, again, in terms of a school, maybe you have ever known that microwaves can be guided in these hollow metal tubes. Maybe you've seen that on the roof of your, where you have your satellite receiver. That's where such a piece always is. And so the basic physics is that if the wavelength is too long, this A should be minimum half a wavelength. But if the wavelength is too long, then the frequency is too small for this, what is called the cutoff point, for the lowest frequency mode, that's the one I depicted here, as you go to lower and lower frequencies, longer and longer wavelengths, you come from a sort of speed of light transmission, you come down in the refractive index to a very, very small number, down to 0, which means it's infinite speed of light. Yeah? So near that cutoff point is interesting, but no time to talk about this. But there, then the index becomes complex. It becomes not, the wave is not existence. It's an evanescent wave regime. So to show this, I once made an experiment where the holes are 50 micron and long in depth, and the width is 8 micron. And so that is the 2A, that means the resonance should happen at about 8 micron, not the resonance, the cutoff point. And as I sent the CO2 laser on that piece of metal, it was gold, sure enough, when we tune the frequency a little bit, we see this very, very steep slope on the transmittance. And the transmittance is really bad, and that means once you are below the cutoff, you can forget it. And that's why you have to forget aperture s-SNOM. And of course, this filter is an interesting application in itself. Okay, so it's all about focusing, and the only focusing we have is the antenna focusing. How is that? How does that work? You could also have a very small particle and pump it into plasmonic resonance and do experiments with that, but the return is very weak. So you cannot pick up any signal which this resonant particle would try to send off. So what you need is a piece of wire connecting this little particle, which does the microscopy, but you connect it with this piece of metal. Why? Because you want to send a wave, which can be coupled here too, send it down as a surface wave. It's a surface plasmon, and that excites the near field, and that also does the job of emitted light will go up here as a surface plasmon and be re-emitted from this antenna. So that is the nice thing we have automatically if we take this metallic tip, cantilever tip from the commercial things. So anyway, this has all the nice things we need. Now, who knows about surface-bounded waves? Maybe I go back 100 years when in our university, Sommerfeld invented a wire wave. He just did an analytic calculation, and the outcome is, oh, if you have a wire, then the light will travel, and if the wire bends around, it will travel around on the wire. So that was, nobody could do an experiment on this, and some years later, one of his pupils, Zenek, he came up with this. So Maxwell's equation gives you a surface wave. If you have a metal and air above, then there is something like you bend the surface maybe down here, and the surface wave will travel around this. But 50 years later, in this paper I found of Gubau, a Siemens engineer, he says, it's the Zenek ground wave is still not, has no convincing experiment up to now, 50 years ago. And now we know, of course, the surface plasmon is what we have on this metal sheet, for example. And if you look at some nice simulation here, not so long ago, if a radar beam scrapes along a mountain top, what happens? Part of it scrapes along here, and you have diffracted light. I think it's Huygens diffraction, well, maybe one calls it. And but there are scattered, apart from those scattered free space waves, there's one wave and that is this one, and please follow. It really moves along the backside of that mountain, and so you have to believe it. So that is a highly confined wave. You see, it's very thin, a thin layer of high electric field, and it's of course a surface plasmon, and it re-emits at these surface bumps, it re-emits light. So my question is, how can a mountain be metallic? Because a surface wave exists when you have a negative epsilon, which is in metals. So who can answer that? Why is a mountain metallic?
Yes, it's the radio frequency, and the radio frequency epsilon might be different.
Yeah, you're right. This is what I'm saying. The epsilon is negative. My question is, why is the epsilon negative of a mountain? It's really a real simulation of some Alps or what this man did. It's because the thing in the metal is the free electron. And so also the material in the mountain, let's say the water in little crevices and the ions in the water, they have some mobility, and there are electrons which have some mobility. And the outcome is there is a plasma frequency which is not as high as visible light, hundreds of terahertz, but it's of the order of 100 megahertz or less. Okay, let's go on. Yeah, another experiment I want to show you because I was very happy to do this experiment. And since I learned from Born and Wolf optics, yeah, I looked up. Born and Wolf says, that's from his book. If you take the metal and you shine on it, then of course on the corner you have these diffracted waves and reflected diffracted waves, these types of orders. But he misses in the whole book that of course you also excite from the corner, you know, because of the K matching and so forth, the surface waves. And surface waves look like that. In the metal there's a little bit, but mostly the field is outside. And it's at a wavelength which is close, but a little smaller than this free space vacuum wavelength. So what I did, take my CO2 laser, send down from above, like here, onto the edge of a metal. This was gold on silicon. And now the polarization has to be such that in the forward direction there has to be an excitation. You see, I shine it everywhere, but only from this edge I send off the surface plasmon, and not from that edge. It's also illuminated, but the polarization has no component in the forward direction in this case. And very nicely to see the damping of the surface wave in one photograph. So my question is now, how can two waves interfere and make such a field, which was a thermal effect of heating the polymer, very thin polymer on here, so that these fringes come out after an illumination of a second or so. How come? How can I interfere a light wave coming from above and a surface plasmon, which is a different mode of light? How can that be? Is it easy to understand or not so easy? The only thing you do in interference, that's why I put this here, you have the two parts of the things you interfere, as you see from the colors. And the main thing is they have the exactly same frequency. And if they have the same frequency, then the time drops out and the wave is sort of permanently stable on the surface, only depending on the difference in K, which is the phase here. And so this is how it works. So remember this formula, we need it for something else soon. Now, how can such a Sommerfeld wire plasmon, which exists, which we excite, how can that superfocus? Because it does, as we know, long wavelengths, terahertz or something, moves down, and the focus is still as small as nanometric, let's say, 100 nanometer, 20 nanometer. And there are two solutions. One analytic, Stockmann, where he just comes to the result, I will show you, and Issa, he was a student even of Rainer, yeah, no, but a colleague in the time we were together, who does a simulation. So he starts with the surface plasmon here and asks, how does it come to the superfocus? And in both cases, you see that the velocity, that's the brown one here, goes to zero. The wave gets slower and slower and slower as you come to the tip. Same here, the phase or group velocities. And but the important thing is the mode radius goes to zero. So there is nearly unlimited strong focusing. Mode shrinks, and gets slower and slower. So in other words, we do not ever observe such a thing, but it is basic to our nanoscopy. That's why I'm bringing it up here. Long ago, before that, it was already clear from this interesting setup, which I used to work with as a postdoc, that if you do a tunneling tip yourself, you just take a piece of tungsten, sharpen it in some KOH, and then with a little spring, make it. Here you have a soldering, and then I just lower very slowly with a micrometer stage to just a polished surface of nickel, which has a natural oxide. So you see with the ohm meter, it comes from infinite out, you come into 100 kilo ohm down to 1 kilo ohm, then it's about right. Then you have about 2 nanometer, which is the normal thickness of this oxide, and then you have a tunneling. So you just do a tunnel, which was much before the tunneling microscope was invented. Yeah? But the tunneling you use, so when you send now your laser, then it will pick up a surface wave excitation here. Surface wave will move down, and it will be so highly concentrating, this 100 milliwatt beam, that you get a tunneling current in the direction such that you can measure on the ohm meter or voltmeter a voltage output. Why is there a rectification? Because the tunneling in one direction, depending on the work function, is happening easier with more current than in the other direction. And that gives you the rectification, very simple. So, but what I want to show you that we measured and used this curve to put the angle right to get a maximum response, having to do with the length of the antenna. Anyway, old stories. What we all know is, of course, all these pictures. I don't even think I should go in any detail. I better look at my watch. And go quickly through it. Rainer will talk about why does the epsilon of the sample influence the backscattering. Yeah, it's this one. I will not dwell on it. But I want to say, I think you have never seen such a simple drawing of our interferometric detection. So I left out the focusing parabola, and then the backscattered light can either go to the detector, that would be direct detection, but you have a signal-to-noise problem or limit. But interferometric means you send half of the power down here and retroreflect it also on the detector. Then you have again these interference powers, and one of them is now the important one. And so you can compare here in the signal-to-noise. Either you have here signal over noise, but you have here signal times reflected field instead of signal to the noise. And so you have a gain of ER over, or 2ER even over ES. So that gain gives you, because you send this strong wave this way, it puts you up by a factor of 100 or 1,000, and that's how you come up into the visibility region for these signals. So we need the interferometry, and we like it, of course, for many other reasons also. And here I just snap in the most cited work we have, and it's a nice thing we are both involved, is interferometry, where the surface wave from the tip on a graphene is reflected at the edge of the graphene, comes back, and so it has a certain phase term, and so you see the first fringe, the second fringe, as you move away with the tip from the, okay. And this is a very interesting application also, because in the graphene you have a mosaic of perfect crystals, perfect crystalline areas, but then you have edges, and so there's another perfect graphene crystal. And at the boundary, you get these interference fringes, and so it's very simple with our microscope to find what is the grain structure of this super-duper material. The broadband coupling is important. How does this work? Because we want a single parabola and a single tip design. The company likes this very much. Wants to work for all wavelengths. Yeah, how can that be? Now look only at the mid-infrared, and I have this factor of 3. This is 1.5 octaves is in this input beam. It's similar of what we have with the broadband. And now the sum of these, let's say the 5 micron, the short wavelengths will be at a much sharper focus of illumination than the long wavelengths part. So that means if you now look at the cantilever tip here and along this wire, the long wavelengths part has a much longer travel distance to do, but it uses a much larger part of this shaft, whereas the short wavelengths uses only the lowest part, but it has only a shorter length to go. And that is a nice complementary or compensation, because the higher frequency waves do not propagate as far as the lower frequency waves. That is well known. And that is how we get more or less a flat response over our broadband. And I show you how our routine, that's a routine work we did recently when we worked on this liquid cell, that we take the broadband as it comes and look at all these harmonics at once, and I plot them here far outside even the region where we normally use it, because here this is a factor of 2 from here to here. This is the typical full width half maximum we have to do our spectroscopy. What I want to point out is mainly that you have this absorption from the atmospheric gases, like the water and CO2. And this is exactly the same in any of these demodulation orders. But if you look closely, and that's what I did and did discover this, parallel to Rainer doing the same thing, or Lars here, but I saw why are there things like this one which do not look the same in every order of demodulation. So what is the reason for that? Who knows this? I mean, here it's the atmospheric transmission. It is, of course, having the same loss. It's in the input wave, so whatever so it's in the illumination, whatever you now look at, the demodulation order, it has nothing to do with this tip oscillation. It's just a far field loss. So why is this different and getting more and more in the higher orders? Huh? It's because it's not a far field, So what else can it be? It's a near-field effect. It's a nice thing. And we looked at it, and somebody immediately said in our group, oh, it's the PDMS line. Yeah. So that means the tip has a little coating of PDMS. And so as you have this in the near field, it depends on how strongly you demodulate that you become it more and more visible. And that was the basis where we said, let's divide one by the other. And I come here to the result. Let's say the green is green by blue, and the red is red divided by this, or the other way around. Anyway, you see, if you divide a ratio, make ratio spectrum out of these spectra, then you can no longer even see where was the oscillation of the atmospheric transmission. It is really nicely referenced out, whereas the PDMS, for example, this one, which we looked at, is strongly there, and it doesn't depend on whether you have this self-normalization 4 divided by 3 or 3 divided by 2. It's about the same result. So I think it's a nice thing we should keep in mind that we have that. Of course, you have now all cantilevers without PDMS, yeah? Is that what the company sells? Can I have 2 minutes, Rainer? So we came up, and we will have 2 posters on that. So I will not go in super detail here. How can we now tap on a very thin membrane? It's only 10 nanometer. Silicon nitride comes from industry very cheaply, already glued to a silicon frame. So that is this thing here. And it is so strong that even when we buy it with a hole of the dimension of 200 micron, a big hole, free standing drum skin, one could call it, it doesn't break when we fill in a drop of water or liquid with some cells, in our case, and then turn it around, seal it, and so we then can go from above, as shown here, with our nano FTIR and scan along it. And the nice thing is that all things we have tried up to now, whether it's polymer micro balls or living cells, then they cling to the surface. We heard this morning the van der Waals is everywhere, so there is a minimum attraction anyway, and there may be specific ways of absorption because cells like to cling somewhere, so they develop some molecules. Anyway, now we found by surprise the surface buckles out a little bit because of that, and we have the nice AFM. The AFM does not see any of the crap down here. It feels only, Lucas, correct me, it feels only that surface. So it is this same kind of interactions everywhere, which I like very much, because you're then free to put in whatever you want here, oil or some things, and you don't make anything bad to your tip. Anyway, it works nicely. We can see cells sitting there. We can. It's all published. We can see where they have special adhesion points and how they develop over time, and we can also go down to that cell at a certain moment in time. I mean, it takes still some minutes to make, I think, a spectrum. But maybe it's going faster in some future, and you very well see the fingerprint spectrum of the proteins and everything. So I come to the end. Show also dynamics. You can have living cells like here, the E. coli bacteria, detach, retach, move, grow, split. And these are my friends in the lab, Thorsten and Enrico. They are both here. And please talk to them and tell them many things they don't know. Lucas, about the tapping, please. And where do we go? Very quickly, my final slide. How deep can we probe? Under the membrane. Go to the poster. What can we learn from distortions? And we go in the direction to look at biophysics, and we need biologists. And with that, I'm at the end of my part. And you can ask me now, if you want. Yes, time. Any questions? And then Rainer will take over.
Thank you very much, Fritz. So, questions?
Thank you very much, Fritz. My question comes to the liquid cell when you, for instance, have different concentration of salts in it. Would it be sensitive to say, well, we can also disentangle through near-field optics different concentration levels of any kind of subphases? So do you say, okay, so let's think about medicine. You take your blood or so, and you're going to analyze that?
I'm sure that you can see it because the dielectric function changes. Yeah? But you think maybe of other things like force gradients, maybe?
No. I'm looking at the dielectric constant. So what would be the concentration at which you say, okay, I'm still confident my near-field signal is really something based on that change of dielectric?
That we have not thought about, but you can think of the same question now in any dielectrics, yeah? And it would be similar. So I think in the like a tenth of a 10% effect or a 1% effect in epsilon gives you surely a contrast which we could pick up.
Thanks.
I have a question on the liquid cell as well. So when the cell comes and binds on the top surface, that's physisorption, right? Okay. So what about if it binds in some other different way, like a secondary structure or folding, or it binds with different aspect ratio, like the length or the breadth of it, will the spectrum change? An FTR spectrum change? Because we have seen like different secondary structures of DNA giving different optical results and FTR results.
I'm not sure whether that would show up, but it depends on the object. For example, the bacteria I showed at the end, they are mostly alongside. What they have is a fur around them. So they can't really touch the surface, but this fur, I call it, something around them, a glycocalyx is the name, has a little contact and does a weak binding. But these cells can turn around, and then they are lengthy cigars and go head-on the surface. And I don't know whether it's known or not, but in our experiment, the signal shoots up. So they are clearly closer, and the surface buckles. So this it depends on the object whether you can play with that. But I think many things. It's fun to work with this cell.
Thanks, Fritz.
Okay, let's thank Fritz again and move to the second part of the talk.